Greetings 101 students. My name's Ryan, and in this video I'm going to tell you about the measurements experiment. Let's start by talking about what the point of this experiment is. This experiment has two major goals. First, it will help you understand what accuracy and precision are. Second, it will introduce you to 4 different pieces of lab glassware and teach you how to properly use and read them. These pieces are the beaker, the graduated cylinder, the pipette, and the buret. So what does the term accuracy really mean? In this course, accuracy means how close a measurement is to its actual, or true, value. For example, let's say you had 2 different 1-cup measuring cups, and you used each one to measure out a cup of water. Let's also say you had some method to determine the exact amount of water you measured out with each cup. This method tells you that you measured out 0.92 cups with one of the measuring cups, and 0.98 cups with the other. Since the second cup came closer to measuring out what its label claims it does, that second cup is the more accurate of the two. As part of this experiment, you are going to evaluate the accuracy of the 4 glassware types we introduced earlier. To do this, you'll use each piece to measure out some water. As you do this, you'll use the markings on each piece to read what quantity of water you are dispensing with it. You'll then use a scale like this one to measure the mass of the water you dispense, then use the density of water, 0.998 grams per milliliter, to calculate the volume of water you dispensed. Now these scales you'll be working with have been checked and evaluated to give you accurate mass readings, so you can assume the volumes you calculate will be highly accurate. Therefore, you will know the actual true volumes of water you measure out. In your post-lab, you can take these actual true volumes and compare them to the volumes you read from the glassware's markings. And by comparing the 2 volumes, you can evaluate how accurate each glassware piece is. Of course, no real science experiment relies on just one data point, so you will take not 1, but 3 sets of read and actual measurements with each piece, and compare the average read measurement to the average actual measurement. Now let's move on to the other measurement concept you'll learn in this lab, precision. Precision is kind of synonymous with consistent, and is used to describe the extent to which multiple measurements vary from each other. Going back to our measuring cup example, let's say you measured out not 1, but 3 cups of water with each measuring cup, and you determined the actual quantity of water you dispensed each time. The first cup actually gives you 0.92, 0.89, and 0.97 cups of water, while the second cup gives you 0.98, 0.97, and again 0.98 cups of water. You can see that the first cup's measurements vary a lot more from each other than the second cup's. In other words, the first cup's measurements are less consistent and therefore less precise. In this experiment, for each of the 3 data sets you collect with each piece of glassware, you will calculate the difference between the actual true volume of water you measure out and the volume you read from each piece's markings. You will then calculate the standard deviation of these differences. The standard deviation is essentially a measurement of how much the numbers in a group vary from each other. The larger it is, the more the numbers in the group vary. For your purposes, it indicates how precise a given piece of glassware is, with a smaller standard deviation indicating better precision than a larger standard deviation. Taking the measurements you'll need for the beaker and graduated cylinder will be a relatively straightforward process, though there is something you need to know about in order to read them properly, and that something is interpolation. To show you how this works, I've got a graduated cylinder here with some water in it, and you can see the bottom of the meniscus, that's the curvy shape the top of the water takes, the bottom of the meniscus falls somewhere between the 27 and 28 milliliter marks. To read this properly, we will use our imagination to divide the space between the markings into 10 segments, and see which of these imaginary lines the meniscus's bottom lines up best with. In this case, it seems to line up best with the 27.5 milliliter marking, so we would read and record this as 27.5 mil. If you're trying to read a piece of glassware and you're not sure what you're supposed to interpolate to, just take the actual physical markings on the piece you're working with and divide by 10. This graduated cylinder's markings go up in increments of 2 milliliters, so you would read and record this one to the nearest 0.2 mil. If you've never done this before, it can sometimes be a little hard to figure out what the value of that last digit is, especially since the lines I put up on the example cylinder don't really exist. Just do the best you can, and don't worry too much if you read a little high or a little low. Interpolation is, after all, subject to interpretation. So coming back to the beaker and graduated cylinder, to take your data, you will first weigh these pieces when they are dry to get their empty mass. You will then fill them about halfway with DI water, and read the glassware's markings to determine how much water the markings say the piece contains. You will then reweigh the piece with the water inside. To get all the data you need, you'll need to do these things 3 times. Oh, and one more thing. Don't try and dry the graduated cylinder by shoving a paper towel into it. You'll never get it out again. Just get as much of the water out as you can by holding it upside down and maybe giving it a little shake. Now you won't be able to put your Buret or Pipette right on your scale, so you'll have to do something a little different for them. To take your Buret data, you'll use it to dispense water into a weighing bottle. First weigh the bottle without any water inside. Next, fill your Buret to somewhere past the 0.00 mil mark and drain a little of the water out, enough to get it below the 0.00 mil mark. There are 2 reasons for doing this. One is it gets all the air out of the spout at the bottom. The other reason is because it is hard, and time-consuming, to get the meniscus down to exactly 0.00, to the point that, for all intents and purposes, it doesn't happen. So if you are truly reading the meniscus properly, you won't have any 0.00 milliliter readings. The next thing you'll need to do is take an initial reading. Since the Buret's physical markings go up in increments of 0.1 mil, you'll read to the nearest 0.01 mil, in other words to the hundredths place, by interpolation. You'll then dispense about 11 to 13 milliliters of water into your weighing bottle and take a final reading, again to the hundredths place. You can then calculate the volume dispensed by subtracting the initial reading from the final. Finally, reweigh your weigh bottle with the water inside. As with the Buret, you'll use your pipette to dispense water into a weighing bottle and weigh the bottle before and after. To use your pipette, you first use a pump to draw water up to just past the pipette's index line. You then take the pump off and use your thumb or finger to hold the liquid up. Then let it drain down to the line and let it gravity drain into your weigh bottle. If you look close, you'll see a small bit of solution will get left behind in the pipette. It's calibrated to account for this, and this is why you don't want to use the pump to force the liquid out of it. You'll note that, unlike the other 3 pieces of glassware you'll work with, your pipette has no graduation marks to read. The amount of water you dispense with it is whatever it's rated to dispense, which is etched or painted somewhere on the pipette side. Just one more thing before you go. The last part of your procedure will ask you to describe what an Erlenmeyer flask looks like. You don't have to take any mass or volume measurements with it, just describe it. And that's your procedure.